the state are arguing autonomous movement and robotic systems. At the present, real-time identification and tracking of 3D objects is deemed suitable. However, the processing bottleneck due to the computational complexities for bundle adjustment makes this optimization. Optimization for these maps is very time-consuming. The bundle adjustment is required to reduce the error of projecting key data points from images and 3D coordinates and reconstruction. So our project focuses on creating a hardware-based graph neural model using FPGA to significantly reduce the time and space complexity of the bundle adjustment algorithm.
Our problem statement, we're aiming to really improve the autonomous vehicle with OrbSlam 2 using Raspberry Pi and Arduino FPGA-based and a Cyclone 5 architecture. Our main implementation is to improve processing, execution timing, trade-offs, and prioritizing human safety.
So our problem definition, we have the Intel RealSense 3D camera that will record and capture nearby objects in 1080p. Using bundle adjustment with the Arduino MKR Vider 4000, we process batches of viewpoints and images to reproduce the most accurate 3D rendition. A graph neural network will then optimize the parameters of the bundle adjustment to reduce the processing time. Location and spatial status of the vehicle will then be mapped using a SLAM generated 3D reconstruction map using the Raspberry Pi. A collaborative effort between the RealSense camera and the sensors will further improve the vehicle's ability to determine position and distance in regard to nearby entities and objects. And the final optimized 3D reconstruction maps are used for computer vision tasks like object identification and determining the travel path.
So for our solution design, as mentioned before, the 3D camera picks up and records the nearby objects, and the Arduino MKR Vider 4000 FPGA uses bundle adjustment to process batch viewpoints to recreate the best 3D renditions. Our graph neural network will optimize the parameters of the bundle adjustment to reduce processing time. And we will use the Raspberry Pi 4 using the OrbSlam algorithm to generate the location and spatial status of the vehicle and generate the 3D reconstruction map. The collaborative effort between the RealSense camera and the sensors further improves the vehicle's ability to determine position and distance in regards to nearby entities. And the final optimized 3D reconstruction maps are used for computer vision tasks like object identification and determining the travel path. And down here, the diagram shows how the components are connected and wired together.
And this is elaborate on I2C connection, used to enable the Raspberry Pi and the Arduino to communicate together using power.
So for our design requirements, the Intel RGB 3D camera, the operating range of the camera is 0.3 meters as the minimum and 3 meters as the maximum, and the weight of the camera is between 60 and 65 grams. The Arduino MKR Vider 4000 has a weight of 43.5 grams. The Raspberry Pi 4 model has a weight of 46 grams. The Raspberry Pi.
You have kind of on ECS for today.
The circuitry wiring weighs between 3 to 10 grams. The battery pack weighs between ½ pound and 2 pounds. And we are also using the Robot Hat PCB3 and the ultrasonic sensor.
You're not going to read, right, in the ECS presentation?
No,
Yeah.
we'll just have it.
So going over some of our constraints, we have our environmental and socio-cultural constraints. So as you know, it has to follow the U.S. roads, missions, and object and hazard recognition that can come up on roads such as potholes, foreign objects. Also, for the socio-cultural constraints, there's still distrust in like autonomous vehicles, just AI in general. And there's also people have their own vehicle design like preferences, so that comes into account. And also, this vehicle has to comply with the NHTSA laws, and also the regional traffic laws in each region, like the DMV area, Midwest, or like Southwest. So.
Here's our drawing, our diagram of our solution design, kind of like the physical design of the base and the connection of the Raspberry Pi and the FPGA and the Intel camera, etc., and the motors. and our component level, more of like a more intricate image or diagram of the actual connection and the components of the autonomous vehicle.
Yeah, here, we started with our first sprint. As you can see, we first started the assembly of our vehicle frame, and right now it kind of looked like a mess, but we generated some improvements to it, and we came up with a Raspberry Pi hash shield, so it can be much more sturdy and on top of the vehicle. Okay, so with our analysis, with the previous first sprint, we concluded that the base is sturdy and it's driving smoothly, and the base can stand all the weight of the components on top of it. But some of the lowlights that we figured out is that the FPGA couldn't fit as planned, and that the base will have to be expanded for the components, because we're gonna add some extra components on the sides for the ultrasonic sensors, and some of the orientation of the wires needs to be changed so everything can be fit and compatible.
So for the second sprint here, we have our data points picked up by our camera. We are using the Raspberry Pi 4 and using AU's SLAM or algorithm to optimize these points to generate the best possible path for our vehicle. This leads to the keyframe generation. Next slide, please.
This is a rendition of a cloud map. The red dot symbolizes the edges of like the image compared to the image over there. The blue boxes represent the motion of the pathway of the camera, and the green box in the center right there represents the position of the camera, like where it is exactly.
So for our current control system, we're using ROS, the robot operating system. For our second sprint, we enabled remote control of our vehicle, and we were developing the prerequisite nodes to enable autonomous navigation. We'll get to that later, but so far we only need the map server, the item in the top right corner, to enable this. Going into our third sprint, we started focusing on the graphical network. We come out across two approaches with two libraries, one with the TensorFlow graphical network and one with PyTorch. This is our TensorFlow approach. This is our data transformation, and based on the paper we were reading, this is our proposed graph structure that we hope to get to within the week, and this is what we have currently. One of the main things is that we lack the aggregators, the mechanisms that will pool our data from the vertex predictors and the edge predictor into one, so we can properly achieve proper cost function. And then we did PyTorch for a simple inference test, not for total optimization of our system, bundle adjustment system. We simply made a few layers with using Sage Convolutional. It's a basic graphical network layer. And next slide. We were able to pass our data through it, which confirmed the validity of our data to be used in a structure like this. So what we have currently with ROS, again, I already mentioned that we only need the map server to enable autonomous movement. Currently, we added the point cloud-based path planners to actually use whatever map we give it to plan its route. We're testing optimization parameters for the D435 processing so that it can keep up to date with whatever mapping services we need. And the problems we're currently experiencing is that our odometry source, the inertial measurement user on the camera, is frequently experiencing clocking issues. The map will occasionally stop updating when we use a combination of OrbSlam and another algorithm called RTAP map. And we're currently combating this by calibrating the camera using the Intel library tools, such as focal length and other intrinsic camera parameters.
Okay, so starting with our hardware implementation, so in order for our FPGA to communicate with the graphical network and bundle adjustment, we had to convert our Levenberg-Marquardt algorithm into VHDL. So as you can see, we went into an application called Vetus HLS. It's an HLS tool that converts MVC files into VHDL. And when I ran it, and compile successfully. And in the next slide, you can see this is our C file from the Levenberg on quad algorithm being converted into VHDL locally.
And then this is the VHDL being used in an application called, one second, ModelSim. Application called ModelSim. And then for ModelSim, I corrected any of the VHDL's errors, and then I'll use coordinates to simulate and synthesize those coordinates. So far, highlights, the car is capable of movement, remote control movement. VHDL has been generated and it is corrected, and there's been pretty successful ROS implementation with some errors to mitigate. Some highlights is the synthesizing car is just taking longer than expected. The infrastructure isn't as easy as to use. We did switch FPGAs, so now there's been a learning curve with that. And it's just been a light setback of the time, but we're hoping to get those done by the end of the week. Here's a video demo.
Oh, you almost there. Go ahead.
Okay, all right. I think your first several slides with heavily small size text, I think you may want to change that. Otherwise, yeah, okay, and then also include do not have, okay.
This
too
is
much
this
heavily text.
is improved. The design implementation is improved.
Yeah, spend some more time, okay, make it really nice slide. Yeah. Okay,
Okay.
all right.